Peace be upon you and God's mercy and blessings. In the last lecture, we talked about the Dyn5 transformer, and we saw together how when a single phase external fault occurs on the red phase on the star side, it draws currents in the yellow and blue phases on the delta side. However, we understand that the current drawn in the red phase on the star side or passing through a coil in the red phase on the star side will pass through a coil in the red phase on the delta side, Dyn5. However, due to the vector group of the transformer and the external connections of the transformer, the current is drawn from outside the transformer through the yellow phase cables and the blue phase cables. Alright, in this lecture we want to address two very important questions. First, the current flow direction in the transformer primary circuit, meaning we want to see how the current flows in the primary circuit of our transformer. Then we will look at the effect of the city connection on the angles of these currents in my transformer and their readings on the relay. In fact, I have been asked these two questions, and they are also very important questions in any interview. So let's take a look together. I took an example here of a Dyn5 transformer, and you will understand through the explanation why I specifically chose this transformer. So, what's the first thing we do? We start by winding the transformer. I brought the core of the transformer and fixed the three primary windings on it, which are the red, yellow, and blue phases, and I labeled the terminals with capital letters. Then I fixed the three windings of the secondary side, which are the red, yellow, and blue, and I labeled their terminal numbers with small letters. Very good. So what do we do next? We draw our phasor diagram. You have A, B, and C on the high side, and A, B, and C on the low side. Of course, up to this point, we are talking about each winding being separate. The windings are not yet connected to each other, and the vector group has not been formed yet. As we know, the direction of the currents in these windings can be in phase or out of phase, depending on the transformer. Polarity, whether it is subtractive or additive polarity. What do we do next? You have now asked me for a Dyn5. What does that mean? It means you want the current on the star side to lead the current on the delta side by how many degrees? 5 times 30, which is 150 degrees. So I start by drawing an angle of 150 degrees here, and then I draw my new phasor diagram with A, B, and C. After that, on this new phasor diagram, I will place my coils, which are the red, yellow, and blue phase coils. I will draw the delta shape, and then I will start to see which of the three coils is parallel to which here. So I have this coil parallel to the red phase coil, this one parallel to the yellow phase coil, and this one parallel to the blue phase coil. I begin to place my coils in this manner. After that, I will place the terminals on the diagram such that A1, B1, and C1 are the internal terminals that will correspond to the star point or neutral, and A2, B2, and C2 are the external terminals that will connect to the transformer bushing. Okay, direction A1, A2, I will find it in this direction. I will start by drawing the terminator here in the same direction as the terminator here, meaning that A1, A2. And let's assume, for example, that this is clockwise, meaning that I will draw another direction clockwise as well and draw A1, A2. And similarly, of course, we will apply the words to B1, B2 and C1, C2. B1, B2 and C1, C2. Okay, so how will the transformer be connected here now? On the star side, A1, B1, and C1 are combined together to form the neutral point, and A2, B2, and C2 are connected to the red, yellow, and blue phases of the transformer's bushing. On the delta side, as we can see, we start with A2. I find A2 with B1 going to IB. I start with A2 with B1, which will go to phase B or be connected to the bushing of phase B in the transformer. After that, I will repeatedly find P2 with C1, continuing this process as needed. Now I know how to make the connection for my transformer Dyn5. Let's take an example. If I have a Dyn5 transformer with a power rating of 60 MVA, which is the apparent power S, with the voltage on the high side being 132 kV, and on the low side being 13.8 kVs. Therefore, the current on the high side is S over root 3V, which gives you 162.43 amperes, and I got a CT with a ratio of 300 to 1. On the low side, it's 2510.22 amperes, and I got a CT with a ratio of 3000 to 1. 301 on the high side, and for the 2510.22 amperes, I got a CT with a ratio of 3001. All right, let's look at the stability condition. To achieve it, we need to choose the appropriate settings for the transformer. So, of course, the compensation side is 0. Okay, for the OT selection, choose number 5. So, how do you get number 5? You have two methods. Either you can deduce it as we saw in the previous lectures, or you can go to the general compensation matrix and substitute the vector k with number 5, which is your vector group. Consequently, you can deduce matrix number 5. Great. Now let's look at the stability condition under normal operating load in this transformer Yn5 on the high voltage side. I will find that my currents, which are compensated or inside the relay, are the product of matrix number 0. In the currents in amperes, which are read of course as the secondary side, meaning after the CT, naturally divided by I nominal to get them in per unit, and the angles are 0, 240, 120. Therefore, the product of this matrix is 1 angle 0, 1 angle 240, 1 angle 120. Now on the low voltage side, I will find that it is the product of matrix number 5, also with the currents 0.8367, which is in amperes coming from the CT, and you have it divided by to convert it. So where did I get the angles from here? 30, negative 90, 150 degrees. Quite simply, we can say the following. Let's see together now. We are on the side where the currents are moving in this direction. So what does it mean that it is in the direction of the current? It will be moving in this direction. Now where is this end connected? It is connected to the current, and thus it means that the end is coming out of the current, which means it will be at 180 degrees in plus. So what is your value? 5 times 30 means 150 degrees. But these 150 degrees mean negative 150 degrees. So what is the sum of this 180? Negative 150 degrees. Therefore, the current that will be read on the relay screen, or it will be used and multiplied by the compensation matrix to calculate the differential quantity, which is 180 minus 150, which is plus 30 degrees. Okay? And of course, for the other phases, you will subtract 120 and add 120. Quite simply, all you need to do is deduce the first phase only. So we need to be careful, because some people, when asked in an interview, might say, oh, here it's 0, so on the other side it's 180. And some people make a mistake and say 0 on the other side is negative 150, forgetting that they should actually add 180 to the negative 150. Negative 150 is the result of the vector group, and the 180 degrees is due to the CT connection, where the start point is towards the protected object. This was of course explained in detail in the previous lectures. Referring back to our references again, the product of this matrix will give you 111 with angles of 180, 60 and negative 60. Therefore, when I calculate, for me, it is the directional sum of the currents which will result in 0. Thus, I have... Alright, let's now look at the stability resulting from the external single-phase voltage on the star side. Let's assume now that I have a single-phase voltage L1 to ground or red phase to ground. How will the current be drawn? It will be drawn like this from A1 to A2. Due to the polarity of the transformer, it will also be drawn in the red phase winding on the delta side, but from A2 to A1. Therefore, where will it be drawn from? From the external terminals of the transformer from phase B and return in phase A. Alright, now let's see where our CTs are. The CT current is here on the red phase. It's the only one that will read the current and send it to the relay for the red phase current. On the delta side, I will find that, of course, the CTs for phase B and phase A are the only ones reading the currents. Before we continue, let's see how these currents will be angled. Of course, the star point CT will be in the direction of the transformer, and as a result of the current passing through the primary cable, the star point CT will be in the direction of the transformer, and thus the angle here is 180 degrees. And thus the angle here is 180 degrees. Nice. Okay. Here I will find mine in this direction, and here I will find mine in this direction. So this means that here it will pass like this. And here also the current moved like this. So it will pass in this direction. So here it is going to the relay dot, meaning 0 degrees angle. And here it is coming out from the relay dot, meaning an angle E of 180 degrees. All right, notice here, what is the phase at 180 and what is the phase here? At 180 degrees, okay, what does this mean? Let's take a look together. If I assume that this is double the quantity, then what will happen? Let's see together. I will multiply by number 5. The current you read is the current double the quantity for you, divided by to convert it. And what is its angle? 180 degrees. And this is the result, or the product of the matrices multiplied together. Okay? If I then move to the high voltage side, 2 phases will be read. Of course, these 2 phases, each phase obviously doubles the current load. And since now I have a current drawn from only one coil, so I have to remember to divide the current by the square root of 3, because the line current now equals the current of what? The phase itself, and divide it by to convert it to, okay, I have double the current over the square root of 3 and divided by to convert, but I will notice that the phase is what? Its angle is 180 and phase B has an angle of 0. And here we will address something very important. Some people make a mistake by saying, I have a tester and I start working with it or injecting with it. And then they say, to represent the differential state, they take it generally and of course applying it incorrectly on the transformer. They say, inject phase red on the high side and phase red on the low side with an angle of 0 and 180, which gives me stability, and I start changing the amount of current until I reach the trip stage. Of course, this is wrong. Why? Because they always think that 0 and 180 will give them the stability condition. Well, I have 2 mistakes. The first mistake is that you ignore the vector group of the transformer. I have a Dyn5, so the phase in the star side cannot be opposed by a single phase in the delta. It must be opposed by 2 phases. That's number 1. Number 2, with this connection, we discover that even if you inject incorrectly, I don't have a problem. You will inject a phase and oppose it with a phase, but you will inject a phase at a 0 angle and oppose it with a phase also at a 0 angle. To give you and change 3 until it gives you, and change until it gives you a trip. So this part is very important to pay attention to. The impact, and this is a point I wanted to convey to you, is that it's not necessarily true. It might be correct in one case, but in the case of a transformer, this is not correct. We need to pay attention to the equipment I'm protecting, plus my relay, and see what my relay's characteristics look like and what the stability condition will look like. We see differential current 2 at 2 over the square root of 3 angle 180 and 2 over the square root of 3 angle 0, then 0, 2 over the square root of 3 angle 0, and 2 over the square root of 3 angle 180, 0. Adding gives 0 and the stability condition in the access programs for the stabilizations, which remain something